Hi everybody. Welcome to another walkthrough practice problem by physacademy.com. In this video, we'll cover a conservation of energy practice problem that has multiple stages. You'll see how the intermediate steps are unnecessary, as the system's total energy is conserved. Let's read the problem statement and analyze it together. A 3 kg mass is sliding down a frictionless inclined plane, theta. The angle of this inclined plane is 22 degrees, towards a spring with constant stiffness of 450 newtons per meter. The mass is initially a meter from the spring and travels at a speed of 0.8 meters per second. Assume the mass of the spring is negligible. So far, we can say the object has an initial kinetic energy as it is moving. Also, there is a height change, so we need to define a reference point and calculate the gravitational potential energies with respect to this reference height. As we have a spring in the system and height change, for sure, we can say this is a conservation of energy problem rather than a conservation of momentum. Question: how much is the spring compressed and the mass is momentarily stationary? The term momentarily stationary means the object's speed is zero at this stage. Therefore, we can assume the object's kinetic energy at this stage is zero. As usual, we start with sketching the system and listing the given variables of the problem. Theta, the angle of the inclined plane, is 22 degrees. The initial velocity of the mass is 0.8 meters per second. The initial distance between the mass and the spring is 1 meter. The spring stiffness constant is 450 newtons per meter. And the mass of the object is 2 kilograms. Breaking the whole problem into the sequence of events, we can say the first segment starts from the initial moment, when the mass is moving at 0.8 meters per second and is 1 meter away from the spring, and its final moment is right when the mass touches the spring system. The second segment starts from this moment to when the spring is compressed, and the mass momentarily stops moving. Let's take the height of the intermediate state as the reference height and then write the general conservation of energy equations of both states. Ke represents the kinetic energy, and Unet represents the sum of all potential energies at the given state. Now that we have the conservation of energy equations, we can use the intermediate state of the system to connect the initial and final states. Rewriting the energy conservation equation, on the left-hand side, we do have a kinetic energy and a gravitational potential energy, while on the right-hand side, we have a spring potential energy and a negative gravitational potential energy as the height of this final state is below the reference height. After writing the formulas, as the height of the initial and the very final state is not directly given to us, we need to replace them. Using the cosine of the theta and d, the initial distance of the object from the spring, and delta d, the compression length of the spring, we get to the following equation. Here besides delta d, which we are looking for, all other variables are already given to us. As you see, the first delta d is squared, and the other is not. This format tells us that we are dealing with a quadratic equation. Let's rearrange this equation into a standard quadratic equation and then solve it. Remember to check the units along the way. As expected, after solving this quadratic equation, we got two answers. One of the answers is negative and doesn't have a physical meaning. But the other positive result with the value of 0.256 meters is acceptable, so we take this as the final answer. Thank you very much for watching this video. Please check our website, physacademy.com, or our YouTube channel for more practice problems. If you found it helpful, please consider subscribing to our channel.